Hello students, I am Dr. Krupa Rasane, Professor and Head ENC, Jain College of Engineering, Belgavi. In this is going to be the second video of Module 4 in the subject of Power Electronics for the 7th semester BE, Electronics and Communication Engineering, VTU. In the Module 4, we'll be looking into the DC to DC converters or nothing but the choppers, and we'll be referring to the textbook of Mohammad Rashid as prescribed by the syllabus. Coming to the content, in my earlier video, the first video of Module 4, we have looked into the DC to DC converter, which is nothing but the chopper. We have looked into the introduction. We have also seen the principle of step-down operation and its analysis with the Rload. In this particular video, we'll be looking into the principle of step-down operation and its analysis with the Rload. And in the forthcoming videos, we'll be looking into the step-up operation with resistive load, then performance parameters and converter classifications. So coming to the principle of step-down operation and its analysis with the RL load, we draw the same step-down chopper as we have seen here. And here, except the load will be an RL load, E is basically connected if the load is an motor. Okay, otherwise E can be removed. Okay, and we can simply consider the RL load. But let me keep E into picture because most often the load that a chopper will be driving will be a DC motor. Okay, so V naught is the output voltage and I naught is the current that is flowing through the load whenever the chopper is on. And also I naught is the current that will be flowing through the load when the chopper is off. But this current, because chopper is off, current cannot flow here. The current will be through this diode, freewheeling diode, which comes into action whenever the chopper turns off. And the energy that is stored, the inductive energy, will get a path through the freewheeling diode because it gets forward biased and the current continues to flow. So basically there are two operations of this particular chopper. As I said, this chopper is basically consisting of other elements, but we are just representing it with a single SCR which acts like a switch. So when this chopper is on, current is going to be carried by the chopper and the load like this. And when the chopper is off, the freewheeling diode FWD comes into picture and the inductive energy that is stored here will be freewheeled through this diode. Okay, so the current will not stop flowing through the load, but it will be a decreasing current whenever freewheeling diode conducts, whereas when the chopper is connected, the current will be of the increasing format through the load. So we can say that there are two modes of operation, and that is mode 1 when chopper is on and the supply gets connected to the load and freewheeling diode is not in picture. Okay, the current flows from the supply to the load, okay, in this particular mode 1. In mode 2, what happens is the chopper is said to be off and load current will continue to flow in the same direction but through the freewheeling diode due to the energy that is stored in the inductor L. So this is the waveform that we are going to look. So if you look at the output waveform, the output will be connected, this load will be connected to the input voltage V whenever the chopper is on, right? So this gets connected here whenever the chopper is on, and that period, as long as the chopper is on, we call it as the T on. And after some time, the chopper is commuted or made to turn off. How does the chopper turn off? Even if the input is DC here, remember, the chopper cannot be commuted, but we have done commutation circuit in our first module where we know that if the input is DC, the chopper cannot do natural commutation, and hence we have to use some commutation technique to turn off the thyristor whenever we want to turn it off. So after T on, once the chopper is on, when I commute it or turn it off, the period for which it remains off is called as the T off. And T will be equal to T on plus T off, which will be called as the chopper frequency, as I have explained earlier in the earlier video. So what happens to the output? During turn on, as I said, the supply will be connected to the load and the load will be drawing the current, okay, and it will be of the increasing fashion and starts from say minimum to a maximum value. And when the chopper turns off, okay, the inductor will change its polarity minus plus, which will forward bias this freewheeling diode. So when the chopper is off, that is in this period, the current will discharge, or the charges stored in inductor will be discharging through the load itself, but it will get a path through freewheeling diode. So the current continues to flow. It will not become zero because chopper is off. The current will continue to flow, but the current will be of the decreasing format. So it will go from I max to a minimum value I minimum. Again during the T on, again I turn on the chopper. So the current is going to rise from I minimum to I max. So this is basically the output current or the output load current. And since this minimum value is reached, it doesn't reach to zero, it reaches the minimum value and carries on from there. There is no discontinuity in the current. Current is continuous. Okay. There is a possibility that if the inductor is not very high, the discharging current may be faster and it may reach the value of 0, and the chopper continues to remain off for certain more amount of time. So the load current will continue to discharge during the off period, but it likely becomes 0 and even before the chopper is turned on, and hence you will get a period when the current is going to be 0 and it appears that the current appears to be discontinuous. Okay, because there is a value of 0 here. So this is a discontinuous current, and here in this case we have got a continuous current flow. So coming again to the analysis, the load current can be continuous or discontinuous depending on the value of L and also the duty cycle D. Okay, in some books the duty cycle is represented as K. In Rashid he has used it as K, but since I am using D throughout the video, I'll keep it as D. So what is duty cycle? T on upon the total time T, where total time is nothing but equal to T on plus T off. So for continuous current operation, which I showed you earlier, load current varies between the two limits, right? So the load current is going to vary from I max to I minimum. When the current becomes equal to I max, the chopper is turned off, right? And it is turned on when the current reduces to I minimum. This is the diagram that we saw in the previous slide. So now coming for the expression. As expression for, we have to evaluate what is the output average current, okay, and as well as output average voltage, okay, and certain other values. So let us analyze this chopper circuit with an RLE load or RL load. You can make E equal to 0 wherever it appears. Now, since I told you there are two modes of operation, the first mode of operation let us look at, and we see that the chopper switch is closed. So this is the chopper switch which has been closed, and the input gets connected to the output, and hence output is same as input. Okay, and this happens when the chopper is on or during the period from 0 to T on. Okay, for the T on period. So this is your mode 1. So if I look at this particular circuit, right, and I want to analyze it, I can write your Kirchhoff's law equation, KVL law. So V becomes equal to I naught into R plus voltage drop here, that is L into di naught by dt, plus this voltage. Okay, so this is the expression we will use to calculate the different current values in the waveform. So bringing the equation forward, I have written V is equal to I naught R plus L into di naught by dt plus E. Now, taking Laplace transform, if you are referring the Rashid book, in the appendix, he has given all the transform values, Laplace transform formula for different components, that is R, L, C, E, etc. So, according to him, if I take Laplace transform, and we know V can be represented as V by S, I naught will be represented as I naught S, R is a constant value, so I keep it R, plus L, di by dt will be represented by S into I naught by S, minus the initial value of current in the inductor. Okay, plus E by S. E is again a voltage, so here we have taken V by S, like that. This will be E by S. E by S. Now, this is at time equal to 0. So, we are considering the initial current, that is I naught for t equal to 0 equal to I minimum, because it begins with I minimum if you have seen the waveform. Substituting that as I minimum here, I will get an expression, take I naught S outside, and I will rearrange this equation in this form, that is V minus E, okay, upon this L. I have got it down, L into S, inside the bracket I can write it as S plus R by L. You can take a pen and paper and try to get this expression in this particular form by substituting I naught at t equal to 0 equal to I minimum. So getting the expression forward, we get I naught S equal to V minus E upon Ls S plus R by L plus I minimum S plus R by L. Now we have to take the inverse Laplace transform. Again, please refer to the appendix T of the textbook, that is Mohammad, Rashid. So taking the inverse Laplace transform of this particular expression, I'll be getting V minus E upon R into 1 minus e to the power of minus R by L into T plus I minimum into e to the power of minus R by L into T. So this is the expression. This is the inverse Laplace transform that we can get. The solution is basically available in the appendix T of the particular textbook. So this expression is valid only for the T on period, that is when T is from 0 to T on. And during this time the chopper is said to be on. At the instant when the chopper turns off, so okay, so the next cycle it is going to go into the off period. That time the load current will have increased to I max, right? From minimum of when t equal to 0, it is I naught equal to t equal to 0, it is I minimum. But when it is at t on, it will have reached the value of I max, as we have discussed in the previous slide. So now coming to the expression for the load I naught for continuous. Now mode 2, let us see, and this is the period when t is equal to t off, that is from 0 to t off. Okay. So this is the time when your chopper is said to be off and the freewheeling diode will be coming into picture. So the equivalent circuit will be looked like this. So this is the freewheeling diode which has closed and chopper has come before this and turned off, so that circuit is not into picture, and the current is freewheeling through the load and the FWD. Okay, so this is the expression. So this is your expression waveform as we have seen, and since it's a continuous current, we see that the current will always go from the minimum value to the maximum value. The initial current, that is at t equal to 0, for this particular off condition, the initial value is going to be I max, right? And a final value at t equal to t off will be I minimum. So this is how we have to look at the initial values. So when chopper is off, that is between T off, we get an expression. See, now we have to draw the KVL expression for this particular circuit. There is no input. Input is 0. So this is 0 equal to R into I naught plus L di naught by dt plus E. Again, I take the Laplace transform like previous. So this becomes 0 equal to R into I naught becomes capital I naught into S plus L into di naught by dt. This becomes S capital I naught into S minus the initial value of I naught plus E by S. Now redefining time origin, we have at t equal to 0. So because we are only considering the t off, so at t equal to 0 means when the t off period begins. That time the initial condition, as I have told you, is I max. So I substitute that value as I max, and I will take the expression for this, replace it with I max, and again rearrange this in this format. So it is easier for me to take it in inverse Laplace transform. Again refer to appendix D, but need not, because now it is very similar to what we have done earlier. So I naught I will get back. I naught of S, when I take inverse, it becomes I naught of T. This is equal to I max e to the power of minus R by L into T. This is the formula. Minus E upon R, okay, into 1 minus e to the power of minus R by L into T. Okay. So this is the expression that we get for inverse Laplace transform, and this is the current equation for the period T. So this expression is valid for the time period T off, that is T equal to between 0 to T off, where T off has been redefined for the off period, and that is during the chopper when it is off. So at the instant the chopper is turned on, when is it going to turn on? At this point, or at the end of the off period, right? The load current, that is I naught off, will have reached the value of I minimum. So I'll take I naught at T off equal to I minimum. Okay. Now we have to find I max and I minimum. So we know in the waveform, for a continuous load current, okay, with a freewheeling diode giving you continuous current, there are two values. One is the I max and the other is the I minimum. Now we have to find the values of these two currents. So from the equation and during the mode 1, we got this particular expression for I naught. Okay, that is the increasing current. So I got it as V minus E upon R, 1 minus e to the power of minus R by L into T, plus I minimum e to the power of minus R by L into T. Okay, where T is nothing but during the on period, that is T on, and T on can be represented as small d into T, or D is called as the duty cycle, right? So duty cycle, which is nothing but, sometimes Rashid has referred to it as K. So you can write it as KT, or this is nothing but DT. That is DT is nothing but T on, right? Because T becomes T on plus T off. Duty cycle is T on upon T on plus T off. So you will be remaining with only the T on. So I naught of T, when at T on, we know it during the first phase, that is T on, when I naught of T, it will reach the maximum value when it is at T equal to T on. So what we'll do is, I will write I naught of T equal to I max, which is equal to V minus E upon R, 1 minus e to the power of minus R by L into T. T will be represented as D into capital T. D is the duty cycle, plus I minimum e to the power of minus R by L. Again, T will be represented as D into T. So this is the expression I am getting for I max. But this I max expression has also the I minimum. So I cannot get an exclusive expression for I max. So what we'll do is try to find what is I minimum and substitute it in this particular expression. So I get an exclusive value for I max, okay, with all parameters known. So I minimum for mode 2, we'll use get this expression for I minimum from mode 2 equation, and we will substitute that I minimum in this I max value. So during the mode 2, we got I naught of t, right? We had another expression there, and that was at t equal to t of, and we got this expression I max e to the power of minus r by l into t minus e by r 1 minus e to the power of minus r by l into t, right? So we are basically looking into this particular continuous load current, and during the off period we had derived an expression for I naught of t. But we know that this is in this off period, when the t becomes equal to t off, at this point the current is nothing but I minimum. So I will, in this expression I will be substituting I minimum is equal to whatever, and t off I will, how t off can be defined? It can be defined as 1 minus duty cycle into the capital T. Again, in Rashid, we are referring to duty cycle as K. Okay, but I have referred it as D. So you should be able to understand all types of notations. So what we do is, I am going to substitute here I minimum and I max, and wherever there is T, I have substituted it as 1 minus D into capital of T. So here also in this bracket, I will be substituting small t as equal to 1 minus D into T. And now substituting for I minimum in equation. So this is your I minimum which I have got in the mode 2, and in mode 1 I had an expression, this expression, where now I can substitute the value of I minimum. Okay, so after I substitute this I minimum here, right? So there is and get the I max on the left hand side, I'll be getting the expression as V by R 1 minus e to the power of minus dRt by L upon 1 minus e to the power of minus RT by L, okay, in the bracket minus E by R. Note that if your load is simple RL, then this E term becomes 0 as it is, okay, and this can be retained for a simple RL load. So I've got the R max value in this particular slide, right? Now, similarly, I want the I minimum value. To get the I minimum value, what I will do is, I have got this expression for I minimum, right, in mode 2. So I will use that expression and try to substitute for I max, which I have got earlier. So by doing that, I get an expression for I minimum as V by R e to the power of dRt by L minus 1 upon e to the power of RT by L minus 1 minus E by R. Right, you can see that these terms have got interchanged for I minimum, and this is the expression for I minimum which is exclusive. It does not have the I max parameter. And what we'll do is, we will find the ripple. Ripple current is nothing but the difference between I max and I minimum. How much it changes from, value changes from I max to I minimum. So that is called as the ripple. Therefore, peak-to-peak ripple current is given by the expression delta I equal to I max minus I minimum. So I have an exclusive value for I max. I've got a minimum value of I max, right? And if they ask you a problem, what is the peak-to-peak ripple current? Just take the difference between them. Similarly, we have already evaluated for a step down output voltage. This is equal to the duty cycle into the input voltage. And average output voltage current can be evaluated by, it's an approximate value, equal to I max plus I minimum divided by 2. Just take the average of the two extreme currents, that is I max and I minimum. You should be getting the average output. So in this particular video, we have been looking into the chopper circuit again with respect to the step down operation, and we have looked into it with respect to the RL load. We have derived an equation for I max and I minimum considering the two modes of operation, mode 1 and mode 2. Also, average output voltage was evaluated previously, but I have noted it down here, and average output current is taken as the average of the two currents I max and I minimum. Okay, so that is how we have completed in this particular video. In the forthcoming video, we'll continue with the principle of step-up operation, or a little more we'll look into the parameters of step-down operations, okay, and RMS value we have not yet evaluated. Then we'll go on to step-up operation and step-up converter with resistive load, other performance parameters, converter classifications we have to look at, and then we will complete the module 4. So thank you for listening, and if you have any questions, please do get back to me. Thank you so much.